Okay, good afternoon. Can you guys hear me? Hello?
Yes, sir.
So there's only two of you, but anyway, I hope others will also come. But still need to discuss. I plan to finish everything this week so that we don't need to have classes Monday and Tuesday of next week. So let's have um, exponential and logarithmic equations today, but we need to go into some other topics first. So we have the natural number defined there. Later on, we will need this to define the natural logarithm and the natural exponential function. And they will be important when we go to solving exponential equations later on by using logarithm. So first, let's define the natural base, e, and it is defined by this quantity or this expression here. Let me read that. E is equal to the limit as n approaches infinity of the quantity 1 plus 1 over n to the n. Now, what does that mean? First, we try to plug in large values of n for this expression and evaluate them. N approaching infinity would mean n is very, very large. And we observe what happens to the quantity as n gets larger and larger. So I have the table here. So for instance, if we plug in n equals 100 here, so we have 1 plus 1 over 100 raised to 100. And we evaluate, approximately we'll get this value, 2.7048, so on. Now, if we observe what's happening to this quantity as n approaches infinity, we'll see that they will be approaching a definite value. And that value is E. In fact, for n equals 1 million, we'll have it equal to 2.71828046991, which is correct to 5 decimal places, 2.71828. Now, if you use even larger values like 1 million, 1 trillion, you'll see you won't get very far from this value here. Now, correct to 9 decimal places, we have the value of E as 2.718281828. You can get that by using your calculator and pressing E raised to 1, or sometimes just E, then the equal sign, okay? So with that, we can define the natural, exponential, and natural logarithmic functions, and we already defined them in general. So the natural, exponential, and logarithmic functions are just those functions to that base E, the natural base. So we have, for the natural exponential function, y equal to e to the x, where e is the natural number. So remember, the other exponential functions that we discussed are 2 to the x, and then we can also have others like 3 to the x, 10 to the x. Okay, somebody sent a message in chat box. Did I not record yet? Oh, I think I did. It's being recorded. Okay, it's being recorded. So that's what we have for the natural exponential function. It's simply 2.71828 to the x, or more exactly, e to the x. And then we also discussed the logarithmic function. One such is the common logarithm base 10. So we have the logarithmic function log x base 10. Now, if you take it to the natural number log x base e, we have the natural logarithmic function, and a spatial symbol for that is this one here, ln x, for natural logarithm. Now let's have just some identities parallel to what we have already generalized for the exponential and logarithmic functions. We also have the following, since they are inverses of each other. Remember that exponential function and the logarithmic function are inverses of each other. So the natural logarithmic and natural exponential functions are also inverses of each other. So they undo each other. So for one, we have ln e to the x equals x. This is exponential base e, logarithm base e. And then this one also, e to the ln x equals x. This is logarithm base e, exponential base e. So we get back to the input number. So ln, again, e to the x is x. E to the ln x equals x. Now let's just have some properties of logarithms. We won't prove the following. Let's just state. First property, logarithm of a product. So let's read. Logarithm of mn base a is equal to the logarithm of m base a plus the logarithm of n base a. Stated in words, we can write or say it as follows. The logarithm of a product is equal to the sum of the logarithm of its individual factors. Okay, this is a product here. This is a sum here. So we say that the logarithmic function converts multiplication to addition, not multiplication to multiplication. So this is not a times, it's a plus. Similarly, we have for our quotient, logarithm of m over n base a is equal to logarithm of m base a minus logarithm of n base a. So logarithms convert division to subtraction with the negative sign for the denominator. Also, we have this property, logarithm of m to an exponent r base a is equal to r times the logarithm of m base a. In other words, you can just drop down the exponent and multiply it to the logarithm of the base m. And as a special case, we have the logarithm of the reciprocal equal to the negative of the logarithm. If you apply this property 2, you can get it as log 1 minus log n, and logarithm of 1 is always 0 as discussed in the previous lecture today, just a while ago. Anyway, you just need to memorize those properties, get familiar with them, and now we will just be applying them to the following examples. So here we have the logarithm, natural logarithm ln, so logarithm base e. So instead of writing base e all the time, you just write ln for shorthand, okay? Ln of the quantity a square root of b all over c cubed d squared. What we want to do is write as a sum or difference of logarithms of the individual factors present there. What are those factors? A, B, C, D. So to be able to do that, we need to apply one or several of the properties given. So let's proceed. We see a quotient. So we apply number 2. We have this. Ln of the numerator minus ln of the denominator. And then we need property 1. We have products for this part, products or product for this part. So we split them up into sums by applying property 1. So for instance, this one becomes ln A plus ln square root of B, which is B to the 1/2. And then this one is a product of C cubed and D squared. So we have ln of C cubed plus ln of D squared. And note that this one is one quantity, so you should put parentheses so as not to make an error in the expansion here. Since the negative is outside, you will have to distribute that over the sum. And then we have this. This came from property 3. You drop down the exponent. So we have 1/2 here, bring it down. That's 1/2 ln b. And then we distribute the negative sign. We have minus, minus. And then drop down the exponents 3 ln c and 2 ln d. And we now have this single logarithm as a sum or difference of the individual or the logarithms of the individual factors present. Any question? Okay, let's do the reverse. Instead of writing as a sum or difference, we have a sum or difference here. We write as a single logarithm. So we will do or apply the properties in reverse. So if you observe the expression here, there's a sum, there's a difference. And remember, logarithms transform multiplication to addition. So if we want to write as a single logarithm, when we see a sum, we convert it to a single logarithm by multiplying the factors there in the logarithms, in the individual logarithms. And we have a minus here. And since logarithms convert division to subtraction, when we see a subtraction, we do division. Okay, when we are converting it back to a single logarithm, as follows. Okay, it's just the same thing. Now we have this. Now, how did I get that? Well, on the numerator, we see the product of these two since they are sums. And below, we see x squared minus 1 since it's a minus or a subtraction. So when you see positive signs, you put them all on the numerator. And if there are more than one, then we multiply them all on the numerator. When you see minus signs, what you do is put them all on the denominator and multiply them all if there's more than one. If there's only one, then you just write it there. So we have this. In fact, if we go back to the previous exercise, if we have this one, notice, okay, this is minus ln c cubed, this is minus ln d squared. They will all, if we want to go from this line back to this line, we will have to put c cubed and d squared below. Why? Since they are both negative after the distribution, of course. And these two have to be put on the numerator since they are both positive. And then they are all multiplied together. So let's go back. So we have this now. So plus, plus, numerator, numerator, minus denominator. Then just some simplifications. So this one, x cancels out, notice on the numerator. So we'll just have for the numerator x plus 1 over x minus 1. And x squared minus 1 factors into x plus 1, x minus 1. And then what happens? Notice that x plus 1 cancels out. So x plus 1 disappears. And then this will be below now, over x minus 1 times x minus 1. So you have x minus 1 squared. Now, this one can also be rewritten as logarithm of x minus 1 to the negative 2. Okay, this is simply a law of exponents where you have the negative as a reciprocal. Remember, a to the negative n equals 1 over a to the n. So to the negative 2 is the same as over square. And why did I do it this way? So that I can just drop that down using property 3. So we have negative 2 logarithm of x minus 1, a single logarithm of the factor or factors present. So we have this as the final answer. Although technically, this one is a single logarithm and maybe considered as already simplified, but we want to exhaust or to make it as simple as possible by just having a linear factor inside the logarithm. And that's by application of property 3, if you have exponents. Now, we will have more practice exercises on Friday. So I will just be leaving those to you to practice on, to familiarize yourself with the properties of logarithms. So we'll go to exponential and logarithmic equations. This is the real stuff now, where in the quiz you expect a lot of questions like this to come out. Now let's start with an exponential equation. By the way, in my previous lecture today, I discussed basic exponential and basic logarithmic equations. So these are the common ones, the say harder ones, or the real stuff, okay? So how do we solve this? 5 to the 2x plus 3 equals 3 to the 2x minus 1. A while ago, in my previous lecture, we solved exponential equations where you can convert to the same base. Like if you have 25 here and then 125 here, you can convert both to base 5. But we can't do that for this one. Now, to be able to solve this, we need to apply logarithms. Remember, logarithms undo exponentials. And we can use any base for our logarithm here. We can use the common base. And I believe in high school, it was taught you how to solve equations like this by taking the logarithm base 10. But since you'll be needing natural bases, or the natural base, natural logarithms in your calculus course after, so we will be using ln to solve exponential equations, given they are not convertible to the same base. So what we do is take the logarithm of both sides. And again, when I mean logarithm, I mean the natural logarithm now. So ln. So if two quantities are equal, their ln's are also equal. So far, so good. Now, the good thing here is that after application of the ln, we can apply the properties to simplify our equation and thus solve. So we have property 3, which states that you can drop down the exponent. So we have the following line. Bringing down to x plus 3, you have here, this one. Bringing down to x minus 1, this one. And notice ln 5 and ln 3 are numbers only. They're like 5 and 3. And what you do is you distribute numbers, right, over a sum. Distribute, distribute. So we have this line. So ln 5 times 2x here, 3 times ln 5 here, 2x ln 3 minus ln 3. So mere distribution. And then we are solving for x, so we will be collecting all x on all terms containing x on one side, all those without x to the other side. So we have this. Okay, 2x ln 5 was transferred on the right hand side, so we have to change its sign, becomes negative 2x ln 5, and then this negative ln 3 transferred here, so it becomes positive ln 3. And then observe that all terms with x are on one side. And once we have that, it is easy to solve for x by factorization of x, since x will be a common term. So we factor out x, we'll be left with 2 ln 3 minus 2 ln 5. Notice if I distribute back x, I get this one here. And then just as is for the left-hand side. So we can now solve for x by dividing everything by this number. This is just a number. No need to use your calculator to approximate that. So just divide by that to get x. And so x is 3 ln 5 plus ln 3 all over quantity 2 ln 3 minus 2 ln 5. Unless otherwise specified, you can leave your answer in that way, in that form. If asked, then you have to give to the appropriate number of decimal places as stated in the direction. Is there any question on that? Okay, none so far. So let's have 2 more examples, and that will be it for this session. Okay, second to the last here. Let's solve that exponential equation. 7 to the x plus 2 times 7 to the negative x equals 3. Now, one mistake students do here is take the ln of both sides and distribute over a sum. Remember, the ln or the logarithm in general cannot only converts multiplication to addition, not addition to addition. So you cannot take the ln of a sum and then distribute the ln. That's a common error students make. So instead of taking that approach, since we do not have times here, if this were a times, it would be easy. Just use ln. Combine the 7 to the x and 7 to the negative x. Actually, it will just cancel out anyway, so this will have no solution if this were a product. But given this, what we do is change our variable, use what we call a dummy variable to convert this equation to a simpler one. In fact, this can be converted to an algebraic equation, or more specifically, a quadratic equation, as we shall see, by using the following transformation. Let u be equal to 7 to the x, because notice 7 to the x is a common term, although this is negative x, but that's okay. Why? If u equals 7 to the x, then 7 to the negative x is the reciprocal of 7 to the x. So it's 1 over u if 7 to the x is u. So we convert everything here in terms of the variable u. We'll have the following. 7 to the x is u. 7 to the negative x is 1 over u times 2. So that's 2 over u. And then equals 3. So now that's simply algebraic, and it can be converted to a quadratic one by multiplying both sides by u. So I multiply the left-hand side by u and then the right-hand side by u. So multiplying the first term, we get u squared. Multiplying the second term by u cancels out, you get 2. Multiplying the right-hand side, we get 3u. So this is a quadratic in u, which is solvable by factoring as follows. Collect all on one side, factor out. Okay, can just later on review this by pausing the video, and then solve for u, 1 and 2. Now this has been solved for u, but it has not yet been solved for x, the original variable. So we take each case. Case 1, u equals 1. And don't forget, from here, u equals 7 to the x. So we simply equate this to 7 to the x and this after to 7 to the x. So if u equals 1, 7 to the x equals 1. And how do you solve this? Just think of a number to which I should raise 7 to get 1. Any number raised to 0 is 1, so x is 0. That should be easy. So 0 is one of the solutions. And then other solution is u equals 2. Equate to 7 to the x. Now, they are not the same. They're not convertible to the same base here. So just take the ln as usual. If we do that, we can solve for x by dropping down the exponent x. And we have that. And then dividing by ln 7, we get x equals ln 2 over ln 7. So there are two solutions. Can just write this inside the set. So 0, the set containing 0 and ln 2 over ln 7, separated by a common. Any question on this part, on this one? Okay. I think this is the last one. Okay. So let's read the problem. Ln of x minus 1 plus ln of x plus 1 equals ln of x plus 11. Now, how do we solve this logarithmic equation? Last two or previous two are exponential equations. This one is a logarithmic equation. We solve exponential by logarithmic or by logarithms. Perhaps we can solve this one by using the exponential, but really there's no need. When you see an equation where you have logarithms for each side, Then all you have to do is apply the properties until you have a single logarithm on both sides. Now, the right-hand side is okay. There's one logarithm there only. But the left-hand side has two logarithms. Let's convert it into a single logarithm. And that's by an application of the properties. This is plus, so we can combine them under one logarithm by multiplying the two factors here. There. So multiplied now, single logarithm. So ln of x minus 1 times x plus 1 equals ln of x plus 11. And since we have both to base e, so if ln of a is equal to ln of b, then the only conclusion is that a is equal to b. Okay? So in other words, we drop the ln's, we simply get or have that. And that's a quadratic equation, which you already know how to solve. Let me just quickly show you the steps. So expansion, transposition, factorization, and then solution. And you have possible solutions for this logarithmic equation, two at the most. Why did I say at the most? Because for logarithmic equations, not all solutions found using the technique are solutions. Some are extra or extraneous solutions. Why? Because the logarithm is only defined when the number inside is positive. You can check your calculator anyway, but if you evaluate a logarithm of a negative number, it's not defined. You may verify that with a calculator, like ln negative 2 or ln negative 1. Although, in higher mathematics, the logarithm of negative numbers are complex numbers. But ln of 0 is definitely undefined. So the ln and the other logarithmic functions are only defined when the numbers inside them are positive. So we will have to check each of the possible solutions here if they are in the domain of each of the logarithmic functions appearing in the original equation. For instance, if we plug in 4, we are all okay since all would be positive. Like 4 minus 1, plug in 4 here, positive. 4 plus 1, positive, so okay. 4 plus 11, positive, okay. But if you plug in negative 3, notice, although negative 3 plus 11 is okay since that is positive, but for at least one of them, like for x plus 1, if you plug in negative 3, negative 3 plus 1 is negative 2. So right away, you can just say negative 3 is not a solution. And actually, so for x minus 1, you plug in negative 3. So both of these two would be undefined. And in terms of real numbers, the equation won't have meaning when we put negative 3. So the only solution for this equation is x equals 4. Are you okay with the explanation? Don't worry, on Friday, if we have the time, I'll try to give more on exponential and logarithmic equations. Tomorrow in my TTH class, I will be discussing the last topic, which is applications. So exponential growth and decay lang yan. So that's it for today, unless anyone has any question at all. If none, then that's it.